So this week's lesson is the sun. So mostly what we're going to do is review the stuff you read on Monday, which is this first section here, and also some of the stuff also from Monday that you worked on yesterday with your pictures, with your posters. So you may have some of it written down, but hopefully we will add a little bit more detail than that. So first of all, let's talk about the sun and the, hang on, and the geocentric model of the sun. Whoops. Okay, so geocentric. Who was it that came up with, or so the geocentric model, sorry, was geo means earth, centric means center. So before the 1600s, this was kind of the general idea that the earth was in the center of the solar system. The earth is the center of everything. And this idea came about just basically by people looking up at the sky. So you look up and you see the moon, which appears to be going around the earth, which it is. You look at the sun, it appears to be going around the earth, which it turns out it is not. But that's what it looks like when you're standing here on the earth. And this all kind of fit along with this model of perfection, and that everything around revolves around the earth, and kind of the perfection of man in the system, and we're the center of everything. Now, it turns out, of course, that when you start looking, especially beyond the Earth and the Moon, you start seeing some problems with this system. And if you look, say, at the planets appear, when you see them in the sky, you probably would just call them stars. So here we have the Earth, and of course, the Moon just rises and sets, the Sun rises and sets. But if you watch the planets, like Venus and Jupiter, Saturn, all of these are bright enough to see in the night sky. And instead of just kind of going in a circle, if you watch any one of them, they seem to rise, and then they might kind of slow down, and then some of them actually almost apparently go backwards and then go forwards again in this very strange movement. And so before the 1600s, there were these really complicated models of how these planets might be moving and wandering and doing all this strange stuff. And that's because they were assuming the Earth was the center of the solar system, the center of the universe, which it turns out it's not. So who was it that that kind of came up with evidence against this idea? Okay, so the first person to actually, the person, yes. Okay, so Copernicus, excellent. So Galileo gets all of the credit for this. And the reason Galileo gets all the credit for it is he is the one that actually published papers and said, here's the evidence I have. And he kind of took one for the team, because it was a really unpopular thing to say, hey, wait, the Earth is not perfect. We're not the center of everything. And it actually got him in a lot of trouble. There were other people before this who thought that the sun was in the center, like Copernicus, who we'll talk about in a minute. But Galileo was the first one to really kind of take a stand about it, which, much like in cell theory, much like in evolution, so he gets the credit because he's the one that actually did that scientific evidence. And again, this is in the 1600s. This is kind of the Renaissance going on in Europe. And as I think I mentioned before, last year you learned about cell theory, you learned about the first cells being discovered, and Hooke and von Leeuwenhoek, and using the microscopes. This is the same time with the same kind of technology. So Galileo has this simple telescope, probably not any more complicated than, in fact, you probably have binoculars that are better quality than what he was looking with. And what he saw a couple things that told him that things were not as everybody believed. One is he could actually see sunspots. And if you look at pictures like this here, this would be roughly what he saw. Again, and I'm not sure if he looked at a projection of the sunlight or if he had dark filters, but you see these here, these sunspots, and what happens over time, this is from today's image on that satellite stuff I've showed you before, and if we look at it tomorrow, they'll be in a slightly different place. And so he could actually see this, and he recorded it. And again, in the time that they're developing cell theory and all that, this is when the scientific method really became developed as well. So he saw sunspots, he recorded them, and he said, you know what? It looks like the sun must be rotating on its axis. Um, he also observed Jupiter, and similarly in his telescope, Jupiter is quite a big planet, and as I mentioned, it's got 70 or 80 moons, but 4 of the moons are very large. And these moons, when he observed them, he didn't know what they were at first, but he looked at Jupiter, and first he would see like a dot here, and then he could see them as they kind of passed across the equator, and he would see these dots, and sometimes he'd see 2, and sometimes he'd see 4 of them, and then they'd be in a different position, and that you can actually look at images of his journals of where he observed this. And so finally he comes to the conclusion that these are actually moons orbiting Jupiter. They're revolving around Jupiter. So this is a further bit of evidence that if Jupiter can have moons revolving around Jupiter, then clearly the Earth is not the center of everything. And we'll talk about this a little bit more next week or the week after when we talk about the planets. So this leads us to the heliocentric model. Helio means sun, refers to the sun. The sun, of course, is made up of mostly helium, so the sun is the center. And yes, Copernicus was one of the first ones who came up with this idea. It wasn't a brand new idea, but Galileo was the first one to really say, look, this is the way it is. I don't care how unpopular it is. I know this is what is going on. And at this time, so in Italy, is where this was going on. The Catholic Church was big in terms of the government and as well as religion, and it was very unpopular to go against the church. And so Galileo himself was actually excommunicated from the church, which you might think, so what? But this was all of the politics and all of the social and all of everything that went around, that was happening, revolved around the church for most people. So Galileo was excommunicated and put under house arrest. Well, you might think, okay, fine, he gets to stay in his house. But this basically meant everybody in his town, his family, his friends, they all gave him the silent treatment. And this went on for I don't know how many years of his life, but basically until he died. People didn't talk to him. He was kind of a non-person. And you know, the rulers, the church told him, all you have to do is say, oh, I was wrong, and you could be back part of the community again. And he said, no, you know, I'm not going to do that. And in fact, the story goes that on his deathbed, his last words were, but still it moves. And so that Galileo, that's why he gets the credit for it. And I was thinking something else and I forgot. So that's the, oh, I know what it was. The Catholic Church finally, and this is really funny, this is never in any of the textbooks, in I believe the 1980s, the Catholic Church said, you know what? And they forgave, that's not the right word, but they, in the 1980s, they formally said, oh, you know what, that Galileo, he was right. I mean, obviously, they recognized it before then, but that was when they formally actually publicly said, oh yeah, by the way, we might have been wrong on that one. So anyway, so that's Galileo and the heliocentric and geocentric models of the solar system. Questions on any of that? Nope. Okay, hang on one second. So the question is if he had such a simple telescope and we have better binoculars, why can't we see Jupiter? You can. There's 2 main problems. One is there's a lot more light pollution now. And because, you know, we have awesome big flat screen TVs and all that, we don't spend a lot of time outside looking at the sky. But you can see it, and you can see the moons of Jupiter. The other thing, too, is he spent a ridiculous amount of time. I mean, every night he watched for the moons and did this, you know, night after night for maybe even years. And again, we'll look at some of that data. But you can see that. You can see Saturn with a relatively simple telescope. You can see Saturn, which looks like it has ears, and those are the rings. But again, when he saw it, and he saw Saturn with ears, he didn't know what exactly that was. But he saw some of the detail on Mars too, I believe. And the ears on Saturn are just the rings. We know now there's rings going around it. And if you ever go The planetarium in Boulder on the CU campus has, star watching, sky watching things. And obviously in the summer when it's warmer, those are good things to go to. All right, we all good with this? The next section that we talked about was what you worked on yesterday, the layers of the sun. So I'm going to go over this relatively quickly so it's in the flipped lesson. However, and then we'll spend a little bit of time at the end of class looking at it. So most of your posters ended up looking something like this, where you have the features in the center and you've got the features on the surface. Now, one of the questions was something like, why does the sun burn? What's fueling the sun? Yeah. Many people think of the sun as being like lava or magma or something actually burning, like a fire. It's actually nuclear reactions, basically, and it's hydrogen fusing into helium, which is putting off a tremendous amount of energy. And it's a little bit mind-boggling, but that's what's happening here. So you've got the core, and all of this is gas. It's not solid, but it's gas, kind of not as we know of, like gas like an atmosphere, but thicker, almost more like, think of kind of a slushiness. That's how the density of it. So you've got the core, where the reactions start, the radiation zone, so vaguely similar. So you've got this, the heat radiating out, the energy radiating out, convection zone, where you've got convection currents kind of like in the mantle. So it all starts here and it goes out here. And then mostly what we see, and kind of more what I'm concerned with, is some of these surface features, which we'll talk about here in just a second. So the question is, if the sun puts off so much energy, is it possible to harness that energy? And to some extent we do with solar panels. Really all life on Earth depends on the energy from the sun, which, you've got plants, trees, all life on Earth, that energy ultimately comes from the sun, and then plants do photosynthesis and trap it. So absolutely, in terms of trapping it for energy use for us, we talked about the use of solar panels and stuff. We can, and usually it's most useful for us if we change it into electricity. We get a lot of heat from it, but like when we talked about energy resources, we can, and then there's pros and cons to that. Mostly solar panel technology can be kind of expensive. You mean like, is the sun going to burn out? Or you mean just day and night? Yeah. And so mostly the solar panel systems, then you store it in batteries and stuff like that. But yeah, it is absolutely. Well, it will burn out, but that's like another 5 billion years, so we're good. We're going to have other problems when it burns out. Yeah. Other questions? Yeah, so basically, like the atom bomb, fusion bombs, fission, atomic bombs, that's basically the same type of energy release. And when you talk about fusion, cold fusion, usually it's very high temperatures, and a lot of the nuclear energy creates radioactive waste, which is a problem. But it is a big energy source that humans have used to some extent, and haven't fully probably harnessed to what we could. Let's look at a couple of these other things. We had the layers, and if you look at these, again, photo means light, sphere, the photosphere, it's the visible surface, and it's also the layer that's putting off light. Chromosphere is a thin layer. I'm not too concerned about that one. And then the corona, it says extending into space. The word corona means crown. And so this, when you're drawing your sun and you have that beautiful sunshine, kind of, like when you're a little kid, you draw all the little rays of the sun. That's the corona. That's the crown. And then I think probably most importantly are these things: the sunspot, the solar flare, and a prominence. So let's look at these three things. These are some of the things when we talk about the active cycles of the sun, when we talk about solar flares, solar wind. A sunspot is actually a cooler spot, which of course appears dark. And these are magnetic, and they'll have kind of a positive and a negative, kind of like a north and south pole that go underneath the surface. And in the one sun picture we look at that I'll show you in a minute, you see them as kind of black and white areas. A solar flare is basically kind of this explosion of all the stuff off of the surface. Exactly what it sounds like, exactly what it looks like. And a prominence is actually a solar flare that just makes a big loop like that. And when you get storms that big, usually those are things that could possibly cause problems for the Earth and other places. So again, here's pictures of sunspots. Again, this kind of is Galileo may have seen it here. This is a closer up. This whole texture, just kind of imagine it as almost, imagine looking at a magma lake kind of thing. And then these are cooler areas, the sunspots. Here's a solar flare. We have much better pictures of these now. The solar flares going up like that. And this prominence, this is actually a huge prominence. And this is actually a very famous solar storm. I think this is the one like from the 1940s. It's very rare that you have one quite that big. These areas here are also solar flares, very active areas. And yeah, basically the solar wind, oops. The solar wind, solar storms. Solar wind, of course, is not wind at all, to be totally confusing. But what it is, it's charged particles. So think of like, electrons, positively and negatively charged things. So it's actually mass like this going off from the sun. And when that hits the Earth, for the most part, the Earth, does anyone know what protects us from the solar storms? The atmosphere to some extent, but from the solar wind, the magnetic field. So the Earth having a north and south pole, and if you could see the magnetic, the magnetosphere as they call it, you could see the magnetic field lines, just like if you had a magnet right here. So this actually attracts the particles. So say the North Pole is positive, all these little negative particles get pulled into here and then release energy as light, and that's the northern lights. And so for the most part, and of course that happens on the South Pole as well. So when there's a lot of solar activity, you might see a lot more, aurora borealis kind of stuff. For the most part, we're totally protected from that. Now, what people might not be so protected from that? Airplanes that are flying up, they don't fly this high, obviously, but we've got satellites up here, right? Our little, GPS satellites, our communication satellites, those are up above this. So if you have a storm with a lot of stuff, think of it as like a power surge, right? If you have a lightning strike, a power surge, it can fry all the electronics in your house. It's a similar kind of thing. So if we know there's a big solar flare, there's a lot, an increase in the solar wind, it could damage all these communication satellites, and then you're not going to be able to text your friends. It's tragic. I know, see? No, but radio communication, also, again, communication, GPS satellites, all that kind of stuff. Similarly, commercial airplanes, they don't fly that high, but they fly high enough that they might be impacted, especially if you're going from United States over to Europe. Depending where you go, some of these flights go over the pole because it's actually longer than going this way, but because that's where all that energy is coming in, there might be a lot more high-level particles. The space shuttle, astronauts who are out traveling, the International Space Station, all of those areas are much less protected. And we don't really know what the impact is of having lots of exposure to this. Probably similar to having too much sun. You might long-term have higher incidences of cancer and stuff like that. So that's what the solar wind is, and that's what solar storms are. And as our society becomes much more reliant on electronics of all kinds, you can imagine that a huge solar storm that's going to disrupt satellites and communication and TV, yeah, like an electromagnetic pulse, that's exactly what this is. So that's why it's important. And the one question on your worksheet that a lot of people didn't get, so when I give it back to you in a little bit, the question that says, how might solar storms affect people on Earth? That's why. And so this, and I'm just about done with our notes here. These are the images I keep showing you from the SOHO satellite, the Solar and Heliospheric Observatory. And there's another one that I'll have to look up. NASA sent up one just a year or two ago that actually is orbiting the sun. So because with this, I told you this satellite is about halfway between the Earth and the sun, and so the only part of the sun we can see is that part facing us, which is all well and good, except you might see something kind of coming on the horizon right here. You're like, wow, is that a big, big storm that's gonna just, you know, explode into us or not? And we can't see that right now. So the other one, and if you look up on the NASA website, you can see images from it. And again, these are all just different wavelengths of ultraviolet light. They're all just different wavelengths. And so you see different kind of parts of the storm from that. And then this one right here actually says magnetogram. And so here you see the positive and negative, the magnetic kind of signature of the solar flares. And then this too. So this you're looking at the corona. We talked about the corona. These are you're seeing the corona here. And in a huge, absolutely massive storm, they have what's called a CME, a coronal mass ejection. And so you'll have like one of those big prominences, except it actually explodes a big chunk of stuff out into space, which would be not so good when it then hits the Earth. All right, so question.